So in this video I want to talk about the asymptotes of rational functions, and in particular I'm going to talk about so-called oblique or slanted asymptotes. So let's just remember that a rational function is a ratio of two polynomials, and I've just written down some arbitrary coefficients here, and we can look at examples a little bit later. Now, there are three sorts of asymptotes. One is a vertical asymptote, which is somewhere where the function here does not exist. So the curve of the function may approach the line here of the vertical asymptote, or it may come away here this way, and such a line is called a vertical asymptote, and it is a line that the curve approaches but never ever touches. So, how do you get a vertical asymptote? As I say, it's where the function does not exist, and that means in this case you are dividing by 0 without the numerator vanishing at the same point. So if we're going to be dividing by 0, we look for zeros of the denominator, and then you will find that your rational function typically does not exist for those values of your input variable x. What about horizontal asymptotes as drawn here? This means that for very large values of x, either positive or negative, our function will approach this constant value. Again, it will never get there, and it will approach it either from above or from below, depending upon the function, and again here either from above or from below. So again, we will see in a moment how that behaves, but this determines or is determined by the largest values of x that there are here. So whatever the largest powers of x are in the numerator and the denominator, they will determine what happens for large positive and large negative values of x. And a slanted or oblique asymptote is a straight line drawn here, where again the function approaches it for large values of x, and again it can approach from above or below, below or above, depending upon the nature of the rational function and the values of the coefficients, etc. So in this video I'm not going to talk about this, but I'm going to talk briefly about this, and then we're going to go on and look at the slanted or oblique asymptotes. So we'll look at horizontal asymptotes on the next slide, and we're going to do this through examples. So on this slide what I want to do is to go through two examples of rational functions and find the horizontal asymptotes that they have. And the key thing to notice that tells you they must have a horizontal asymptote is that the largest power of x in the numerator is the same as the largest power of x in the denominator. So let's look at this function, and I'm going to divide both the top and the bottom by this highest power. So if we do that, we are dividing the top and the bottom by a power of x squared. So in other words, we're not changing the function. You know, if we divide the top and the bottom by the same thing, this is still f of x. So we get f of x is equal to, and now if I divide 6x squared by x squared, I get 6. The next term I have minus 1 over x, and then the next term I have plus 9 over x squared. And on the bottom I have 3 plus 8 over x minus 1 over x squared. And writing it in this way is, generally speaking, not helpful, but for this one point about looking at the horizontal asymptote is very useful, because we can recognize now that as x approaches plus or minus infinity, it's going to become, in other words, when it's becoming very big, Well, we'll have a 6 here, but this is going to go to 0. This is going to go to 0 when x is very large. So we've got a number divided by something very big, it's going to go to 0. And the same is true here. So therefore we see that as in the limit, as x goes to plus or minus infinity, f of x is going to go to 6 plus 0 over 3 plus 0, and 6 over 3 is 2. So if we were to sketch the function, I can't tell you more about it, but I can say that this line is going to be a horizontal asymptote where the value of y is 2. I can't tell you whether it approaches it from above or from below without thinking about it, but this line is a horizontal asymptote. So, having gone through that example, what we can do is look at the next example here. And if you wish, you could just pause this video for a second and work it out for yourself, and then just carry on to see that it's... Well, we look at the highest powers of x here. Here it's x cubed, here it's x cubed. So we can divide the top and the bottom by x cubed. So again, effectively all we're doing is multiplying by 1, but in a way that's helpful. So we're dividing the top and the bottom by x cubed, and that tells us that g of x can be written, and this is an algebraic identity, as 2 minus 1 over x cubed, all divided by 1 plus 6 over x squared minus 4 over x cubed. And now again we can say we recognize that as x is going to approach plus or minus infinity, g of x, the function, in the limit as x goes to plus or minus infinity, is going to approach 2 minus 0 over 1 plus 0 minus 0, which I'm not going to bother to write. In other words, it's going to approach 2. So in this example, if I just draw some axes, x and y, again we have, as x approaches infinity, our function is going to approach 2, and again as x approaches minus infinity, it's going to approach 2. So this is a very standard way of calculating asymptotes of rational functions, and on the next page I'm going to apply it to slanted asymptotes and see that we have to be very careful. So let's move on to the next slide. So on this slide what I want to do is to calculate an example of a slanted or oblique asymptote, and the function that I'm going to use for this is written here. It is x squared minus 1 divided by x plus 2. So what we can do immediately is use the techniques of the previous slide. So from before, what we would tend to do is to say our function is x squared minus 1 over x plus 2, divide top and bottom by the smaller of the two largest powers of x. Here we have x squared, here we have x, so we would tend to divide top and bottom by x, and we will obtain x minus 1 over x when we divide the minus 1 by x, and on the bottom we have x plus 2 all over x, so we obtain 1 plus 2 over x. And this is an algebraic identity, and nobody can argue with that. The dangerous step is if we now say the following. So we might claim that as x approaches infinity, f of x is going to approach x minus naught over 1 plus naught, so it's going to approach x. So what we've done here is we've said as x becomes extremely large, we have x, which will be large, minus something which will become very small, it will tend to 0, over 1, plus something which will also tend to 0 as x becomes extremely large. So we have x minus naught over 1 plus naught, and that's going to approach x. And this is not true. So what I want to do in the rest of this slide is to explain what the issue is and calculate it correctly. So let's just see what the problem is. So f of x will actually approach, as x approaches infinity, it will approach x plus a constant. So if you think of this as x to the power 1 plus a constant which is x to the power of 0, this is a leading term in x, as it's the highest power of x. And this technique has identified that correctly, but this constant term, x to the power 0, this is a subleading term in x, and it misses it. So we have to see what we've done wrong and how we obtained this. So to do this, let's consider how we've written the function already and just rewrite it very slightly. So f of x is equal to x minus 1 over x, I'm just rewriting it slightly, all in brackets, multiplying 1 divided by 1 plus 2 over x. So this is exactly the same as what we have here, and I'm just writing it in this way because what I want to do now is to rewrite this, multiply the two together, and we will obtain x, but we will also obtain the constant. So how are we going to write this? Well, there are different ways. If you know the Maclaurin expansion technique, you could use the Maclaurin expansion, and that's something that I would encourage you to do separately. However, what I'm going to do is I'm going to recall an algebraic identity and obtain an expression for this. So the identity that I want to recall is the following. So if we take 1 minus something which I'm going to call here epsilon, and we multiply it by 1 plus epsilon squared plus epsilon cubed plus etc. up to epsilon to the n, when we multiply this out, we're going to get 1 times 1, and then we're going to get terms such as 1 times epsilon, which will give us an epsilon, but we're also going to have minus epsilon times 1, and they will cancel. And you can just work through this if you don't know the identity and see everything will cancel except for minus epsilon times epsilon to the n, and that will give us minus epsilon to the n plus 1. So this is an algebraic identity, and now what I'm going to do is assume that epsilon is small. Remember, here we're interested in x becoming very large, so 2 over x is a small quantity. So we're interested in epsilon being small, and I'm going to allow n to become very large, and as n approaches infinity, this term here is going to go to 0. Just think about having a half, say, and multiplying it together repeatedly. As you keep doing that, more and more times this gets smaller and smaller and will eventually approach 0. So what we have is 1 minus epsilon times 1 plus epsilon squared plus on forever is equal to 1. and that tells us that 1 over 1 minus epsilon is 1 plus epsilon squared plus epsilon cubed, etc. on forever. And this is also, if you know the idea of Maclaurin expansions, the Maclaurin expansion for this for small epsilon. So this is our result. I'm now going to say let epsilon be minus 2 over x. Let's be careful with the minus sign. Here we have 1 over 1 plus 2 over x. So plus 2 over x is minus epsilon. So epsilon is minus 2 over x. And now I want to put this into this substitution here and put that into here. So therefore, f of x is x minus 1 over x, brackets, all multiplying, and now all we're doing is rewriting this using this relation with epsilon being minus 2 over x. So we obtain 1 minus 2 over x plus minus 2 over x all squared plus, and then it's higher powers of minus 2 over x, and I'll close the bracket. So at the moment this looks very complicated perhaps, but it's about to become simple. So what we do is we just multiply this out. We take this bracket times this bracket, we get x times 1, so that gives us an x. We have then got x times minus 2 over x, so this is minus 2x over x, and that is a wonderful term because you can see that the x's will cancel and that we have got a constant, and this is exactly what we were missing up here. The x term is correct, but there is a subleading term, a constant, and we get that by expanding this, multiplying it with the x here, and then when the x's cancel we see we are left with the subleading term. Basically this is becoming very large, this is approaching 1, but the correction to the 1 multiplied by the x here gives us a constant. Now, what about all the rest of the terms? Well, the good news is that all the rest of the terms are irrelevant as x approaches infinity. So I'm just going to write down plus order 1 over x. And this notation simply means that everything I'm not bothering to write down has at least one power of 1 over x in it, and therefore as x approaches infinity, which remember is what we're interested in for the asymptote, this will go to 0. So why is it that everything else goes as 1 over x? Well, here I've got x times 1 was that, x times this gives us this, but x times this term, well here we have effectively an x squared in the bottom, and x times 1 over x squared will give us a 1 over x. The next term I've not bothered to write here involves an x cubed on the bottom. X times x cubed on the bottom will give us 1 over x squared. Again it will vanish. All of the higher terms will vanish. Here we have minus 1 over x times 1, that goes as 1 over x. 1 over x times 2 over x goes as something over x squared. Again it will vanish. X on the bottom, x squared on the bottom will give us an x cubed on the bottom. All the other terms are negligible. They tend to 0 as x approaches infinity. So what we see is that f of x as x tends to infinity approaches x minus 2, because again back here the x on the top and the x on the bottom cancel, and we were left with x minus 2. So this is our result, and this is the slanted asymptote for this function here. So the technique that we used before is absolutely correct for the leading term, but it can miss subleading terms, and this is how we can find them. Now, another way of finding them is to use polynomial division, and that's what I want to do on the next slide. So on this slide I want to use polynomial division to obtain the large x asymptote of this function. So this is an improper rational function. The highest power of x here in the numerator is higher than the highest power in the denominator, and we can use polynomial division to write this as a polynomial plus a proper rational function. So to do that, what we're going to do is take x squared minus 1, but I'm going to write x squared minus 1 as x squared plus 0x minus 1, just to help myself a little bit, and we're going to divide this by x plus 2. Now, this works just as normal long division does, and I just take x plus 2 and I multiply it by something which will give me the leading term, and then I have to subtract that much. So what do I need to do? I need to multiply x plus 2 by x, and x times 1, so 1x. So if I do that, I get x squared plus 2x. And here, since I've multiplied my denominator by x, I write an x. I then subtract, the x squareds will cancel, that's what we set it up to do, and we have 0x minus 2x, we have minus 2x. I'll now rewrite the minus 1 here, so I write that as minus 1, and now I recognize that if I again want to divide this into here, I need to multiply the x here by minus 2, so I'm going to write minus 2 here, and I write minus 2x, and then 2 times minus 2 is going to give us minus 4. So now we subtract these, and again by construction the minus 2x's will cancel. We have minus 1 minus minus 4, so that's minus 1 plus 4, so that's going to give us 3. So what we see, our result, is that x squared minus 1 over x plus 2 can be written as x minus 2, that's our polynomial, plus 3 over x plus 2. And that result makes it absolutely clear what happens for large values of x, because when x becomes large, 3 over x plus 2 is going to go to 0, and we will be left with x minus 2, which was the result on the previous slide. So what we see is, if we draw a set of axes for this function, we have the line x minus 2, y equals x minus 2, crosses the y-axis at minus 2, and this will be the large x asymptote. So it will approach it this way or this way, and this way or this way down here. So, can we check this in any way? Yes, we can, and I think it's a good thing to do. If we look at the right-hand side of this equation, to check our polynomial division, all we need to do is to put these terms together on the common denominator of x plus 2. So let's make this check. Check. So, x minus 2 plus 3 over x plus 2 is equal to all over x plus 2. So we have x minus 2 times x plus 2, and that of course is just this first term. The x plus 2's cancel, we're left with x minus 2 plus 3, which is this term here, 3 over x plus 2. We expand this out, we get x squared, the cross terms will cancel, minus 2x plus 2x, and then we have minus 4, so we have x squared minus 4 plus 3. So this is x squared minus 4 plus 3 all over x plus 2, and just tidying that up a little bit, we have x squared minus 1 over x plus 2, and that is our original function, so we know that the polynomial division was calculated correctly. So that is another way of obtaining the large behavior, and it's the safest way of calculating oblique or slanted asymptotes. And with that, I will stop this video.